On this video, let's talk about a special kind of solid, what's called a solid of revolution. So if we take a region in the XY coordinate plane and we revolve it about an axis, say the x-axis or the y-axis or any horizontal or vertical axis, what we get is a solid of revolution. And we can see this visually. I have a little picture here that I created. If you have a region, you can see here it's a region in the rectangular coordinate plane. Here's your x and your y-axis. And if we revolve that region, so literally think of this as think of that region as basically scraping out a solid, coming out and revolving 360 degrees all the way around the x-axis and creating this sort of almost like a funnel like, but it's totally solid. This is solid in here because that region was solid. That is what we call a solid of revolution. It is a solid that was created by revolving a region around an axis. Okay, so how would we find the volume of such a solid? Well, what we're going to do is we're going to do the exact same thing we did in the general slicing section of this unit. When we calculated volumes using general slicing, we just sliced up the solid and we looked at what a cross section would look like. So we're going to take a slice. Okay, there's one slice, here's another slice, and we're going to think about what does that slice of this solid actually look like. And it turns out there's only going to be two options. It's either going to be what we call a disc or a washer. So you can see right here, if we were to pull that slice out, that slice looks something like this. It's solid. It has some thickness. We're along the x-axis, so that thickness down here, the thickness of the slice is what we say is delta x, and we do, remember in that Riemann sum, let that delta x go to 0. And this area right here is what we'll have to figure out. We'll have to calculate the area of that slice. But for a disk, it's pretty easy because a disk is a circle. The area of a circle, the cross-section of a disk, would be the area of a circle, and the area of a circle is just pi times the radius squared. So that's what we'll do. Turns out that sometimes when we do solids of revolution, we actually get what are called washers, where we have a little hole in the middle of the disk, and it's a washer rather than a disk. But again, that's an area formula that we'll be able to set up and compute. So let's look at a little 3D image here, just so we can see a prettier dynamic picture of a solid of revolution, and then we'll come back and generalize these formulas. Okay, so here's a dynamic image in the textbook, the interactive textbook. And what we can see is if we take this region right here, you can see actually it's showing me some points of this curve. But if we take this region bounded by f of x and the x-axis along the interval from x equals a to x equals b, if we take that region, let's go ahead and go all the way back to the beginning. If we take that region and then we kind of spin the xy axis kind of at a bit of a diagonal so that we can actually look at it better, so we can see it, and we revolve that. I'm going to go ahead and drag this. We're going to revolve that. We're going to send that region all the way around the x-axis, revolve it around the x-axis to create a solid. And you'll see that happening over on the right side of the screen. So there you go. That solid is being revolved, and you can see that solid that we want to look at, we can calculate the volume of that solid by taking a slice and calculating an area formula for that slice, and then adding up all the slices and letting the number of slices go to infinity, which gives us that definite integral. So let's take a look at what a slice would look like. Okay, so that same region here. This time, though, you can see a little bar here at some generic x between a to b, and you can see that same x over here in the solid that we're going to create. Now let's go ahead and let's revolve that solid around. And as we revolve the solid, there it goes, it's going all the way around. And now the image has lightened the actual solid, so you can see that cross-sectional piece at that generic x. You can see that that's going to be a disk. And we do know that the area of a disk, so the area of that cross-sectional piece, is pi times its radius squared. Well, how would we calculate its radius? Well, that's where we come back over to the region, and on this particular graph, the radius of that disk, because the height of this little piece that got rotated around, is going to give us that radius. So the height of that little piece is f of x minus 0, because the lower bound of it was the x-axis. So let's do an example of this. Let's find the volume of the solid that is generated by rotating a region bounded by y equals x squared, x equals 0, and x equals 2 about the x-axis. So we're going to go ahead and derive some steps here, and then we'll summarize them at the end of the video. So the first thing we're going to do is we're going to draw the region. So we're going to draw the region that we're going to be revolving. So again, this particular graph is going to be an easy one to graph because y equals x squared is just a parabola. So we've got a parabola y equals x squared. I'm not putting the scale on here. We're going to go from x equals 0 to x equals 2. We're going to let this be 2 just so I have some space. Actually, that worked out pretty good because that would be a 4. So then we'll let the y-axis be like that. So we've got the vertical line, x equals 2, the vertical line, x equals 2, which cuts it off right there. And we actually have the horizontal line, y equals 0, because since we are revolving about the x-axis, that is creating a bound for the region as well. So the region that we're revolving is this region right here. And we're revolving it about. Now, that's the other piece. When we're drawing the region, we also need to determine on that graph where we're revolving it. And we're revolving it about, so this is what we call the axis of revolution. So we're revolving this region around the x-axis. I should have labeled x and y-axis. So let's do that. So we're revolving around the axis. The axis of revolution is the actual x-axis. That's where we're revolving that. So that's the first thing we'll do. And then we're going to do our best to draw the solid. So we can figure out what is that going to look like. So we're going to do our best to draw the solid. Now, the solid here, and I'll do my best on this little virtual whiteboard here. Here's the x-axis. We're taking something that looks like that, and we're revolving it about this axis. So, one of the ways to do that is to mirror it, because we're going to have it mirrored down below. So one of the ways to do this, I'm actually better at doing this in pencil than I am in whiteboard pen. One of the ways to do it is mirror it across the axis of revolution, and then think about it in 3 dimensions. So this right here, because it's going all the way around, is going to create almost like a funnel-like shape, like that earlier image that I had. So it's going to create something that looks like that. I'm going to go ahead just to make it 3-dimensional. I'm going to show a couple more little diagrams right there. So that is what the solid is going to look like. And this is solid. Like this is all the way solid, right? That's a complete solid-like funnel that we're looking at. Okay, so that's the next step we do. We draw the region, we draw the solid, and then what we're going to do is we're going to make a cross-sectional cut, and we're going to do it perpendicular. So we're going to cut, I'm going to do it on the graph, but I'll write the step right here. We're going to find a cross-sectional piece perpendicular. So that is important. Perpendicular, I'm using the little notation there for perpendicular. So perpendicular to the axis of revolution. So I didn't draw the axis of revolution, I just revolved, but let's go ahead and put that little arrow there just to indicate that axis of revolution again is around the x-axis, axis of revolution. So we're going to make a cut perpendicular to the axis of revolution. So I'm going to come in here and I'm going to make a cut. And actually when I was drawing that 3-dimensional piece, I did get a little cut. I'm going to make a cut and we can see right there that the cross-sectional piece I'm going to just call it cross-section instead of saying cross-sectional piece. The cross-section is a disc. The cross-section right there, make it bigger over here, is a solid disc. So we also need to think about when we make that cut, since we're cutting perpendicular to the axis of revolution, we need to think about the thickness of that piece. Is that going to be a delta x or a delta y? Because we are going to revolve around horizontal and vertical axes. And so when we do that, we can set these up with respect to x or with respect to y, depending on the thickness of the slice. Now this thickness of this slice right here is a delta x. So remember, we do have a little bit of thickness when we're cutting these slices. Now, when we apply the limit as n goes to infinity to the Riemann sum, that thickness goes to 0, and we get our definite integral. But this will tell us this thickness if it's with respect to x or with respect to y, if the integral is going to be with respect to x or with respect to y. Okay, so how do we calculate the area of a disk? Well, the area of a disk, and it is going to be in terms of x, the area of a disk is always just pi times the radius squared. So the area of a disk is pi times the radius squared. So now we have to figure out what is the radius. Well, the radius, here's the axis. Let's go ahead and put that little dashed line in there on my disk, my image of the disk right there. There's that axis. Would come straight down the center of that disk. The axis of revolution comes straight down the center of that disk. And so this height right here is the radius. Now, I drew it in red on my picture over here. I should have probably just, let's go back and make it in black. This little slice right here is in black. It's just zoomed in over here where I said cross-section is a disk. So let's draw the red radius right there. So how do I calculate that radius? Let's go all the way back. This is why it's good to have it here as well. Let's go all the way back here. This is where the radius is coming. That's what's getting revolved. So that is the radius of the disk that we're trying to calculate the area of. So if that's the radius of a disk, how do we calculate that? Well, the radius, let's think about the actual graph that we're looking at. This was the curve y equals x squared. So the radius is going to be equal to x squared, right? The top of that radius minus the bottom, which is 0. And I will write that. I think that corresponds nicely with when we were calculating areas, right? Function on the top minus the function on the bottom gives us that height, that radius right there. So the radius is x squared, and I can plug that back in over here. So the area function is pi times x squared squared, which of course is just pi times x to the 4th. Okay? So we draw the region. Let's label where we're at so far. We draw the region, we draw the solid, and we determine what a cross-section looks like. After we've determined what the cross-section looks like, we calculate or set up its area. Okay? We calculate a formula for its area, the area of a generic cross-section. And then the 4th step here is going to be to set up the integral to calculate volume. And I zoomed way out so I could get it all on the page here, but I'm going to have to zoom in a little bit. I'm going to keep the area formula there. So remember, when we calculate volumes of solids, the general slicing method says that if you can calculate the area of a cross-sectional slice, which we just did, it's a disk, then it's going to be a of x dx across the bounds from A to B, where the solid lies. Well, our solid lies, let's get back to our picture, our solid lies between 0 and 2. So 0 and 2, I didn't actually put that over here. This is 0 and this was 2. That's where the solid lies. So this is going to be the integral from 0 to 2. Our area function, we calculated, pi times x to the 4th dx. And that's how we can calculate the area of this solid of revolution. So this is a simple integral just using our basic integration strategy. So let's go ahead and do it. It's going to be pi times x to the 5th over 5. And we're going to evaluate that from 0 to 2. And so we're going to end up with pi times 2 to the 5th, which is 32 over 5 minus 0. And so our volume of this solid is going to be 32 pi over 5 units cubed. And that is the volume of the solid of revolution using this process that we're going to follow for solids of revolution. So for solids of revolution, I'm going to summarize it on the next page, but I did just put it all here in the steps as well. Okay, so here are some outline steps typed up. Oops, it kind of went off the screen a little bit. Typed up here. So what we're going to want to do is to find that volume of a solid of revolution, we draw the region that we're going to revolve. We revolve the region around the specified axis and sketch that solid of revolution. Now, I do say sketch right there because, you know, these aren't going to be some of you may draw amazing three-dimensional graphs, but that solid of revolution is three-dimensional, and we do want to have a visual of it so we can see if the cross-sectional slices are going to be discs or washers. So the next step is then to determine, is the cross-section a disc or a washer, and what is its thickness? When we take that cross-sectional slice, those cross sections, by the way, are perpendicular. So we do our cross sections perpendicular to our axis of revolution. So when we do that, that's when we determine if the thickness of that cross section is a delta X or a delta Y. And then depending on if it is also a disc or a washer, we set up our area formula. So the area of a disc is pi times the radius squared, or pi r squared, and the area of a washer is pi times the outer radius squared minus the inner radius squared, or pi times, I sometimes like to use this notation, r sub out and r sub in. So we determine those radiuses from the actual graph of the region. So then we go back, determine those radiuses from the graph of the region, set up the integral, and compute the integral. I think I stopped writing steps as we were working through the example, but we did all those steps. Okay, we haven't seen a picture yet of a washer, but let's go ahead and summarize what I was just saying right there with a couple of images. So this is the one that we just did. We just did a disk, the area of a cross-sectional slice. If it's a solid disk, then we're going to be using the formula pi times the radius squared, depending on if the cross-sections are vertical with a thickness of delta x or horizontal with a thickness of delta y. Our area formulas will correspond and either be with respect to x or with respect to y. Now, if we have a washer, so this is the one we haven't done yet and we'll do next. So if we happen to have a washer that we're working with, and we take a cross-sectional slice and there's a hole in the middle, right? If we could like stick our hand through the hole in the slice that we're taking, if it has an opening in the middle, then we calculate the area by simply taking the area of the outer circle and subtracting the area of the inner circle. And that gives us this formula, pi times the outer radius minus the inner radius. And you can see here, I've outlined on here, I drew some pictures of washers. With thickness delta x or thickness delta y, and looking at, but you go back to the original graph of the region that was revolved and determine how to calculate and set up the outer radius and the inner radius. So we'll practice that for sure. But once we have that formula of a washer, then to calculate the volume of a solid, we simply integrate that area formula, either with respect to x, if our thickness of our washers are delta x along the x-axis, or if they're delta y, we use an area formula in terms of y. So I'll leave that on the screen for a second if you want to screenshot that or take those notes. Those are nice formulas to have in your notes for the area of a washer. And again, the area, I don't think I paused up here, so maybe I'll pause here for just a second if you want to grab those for your notes as well. The volumes of a solid of revolution where the cross-sectional slices are disks. Okay, let's do one more example where we have a washer before we end this video. Okay, let's do one more solid of, let's compute the volume for one more solid of revolution before we end this video. So let's do this one. Let's find the volume of a solid that is generated by revolving the region bounded by y equals the square root of x and y equals x about the y-axis. Okay, so our first step is to draw the region. So the square root of x is going to look something like that. I zoomed way in because this is actually going to be like a little tiny solid. So here is y equals the square root of x, and then the line y equals x is just the line through the origin and through 1, 1. So that is going to be, let's make that dot really big so I don't have to redraw that line. That line actually goes on, but the square root does not. So when we're talking about the region that is bounded, so this is the line y equals x. So when we're talking about the region bounded by y equals the square root of x and y equals x, this is the region right in here. That's why I had to zoom way in, because it's just this little tiny sliver. But we want to take that and create a solid by revolving that about the y-axis. So we're going to revolve about the y-axis. So I use my little arrow there in red to indicate the axis of revolution. So the axis of revolution is the y-axis. So let's see, what would the solid look like if we do this? So we're going to revolve that little sliver around the y-axis. And for a visual, I might kind of make it a little bit bigger. So we're going to take that region. Now, I'm going to have to dash this guy out. I'm kind of making it a little bigger maybe than it is. I have to dash that out because when I revolve that, again, think of that region over here on the left side of the screen. Think of that highlighted region like coming out towards you and revolving all the way around just to eke out a solid. And so, when you're drawing your solids of revolution, you could think of, mirroring that image and think about what you can see and what you can't see. You can use dash lines like I'm doing here. And that's going to be behind the wall of the solid. And we're going to create this almost like a vase that I could, like, you can't see me right now, but well, here, I'll do a highlighter. Almost like a vase that you could like put your hand into, but the walls of the vase have some thickness to them. Okay, they kind of bulb out on the sides. So that is what our solid looks like. And our axis of revolution is right here on the y-axis. This is our x-axis, this is our y-axis. So that's what the solid looks like. The next thing we want to do is we want to make a cross-sectional slice perpendicular to the axis of revolution. So we're going to come in here and we're going to take a little slice of this solid and think about what does the area look like. But because of that hole essentially in the middle, we get a washer. So a cross-sectional piece actually looks like a washer in this case. Explanation, explanation. So it's going to have, right? So here's the washer. The washer is going to look, I'm going to just make it bigger over here so we can see it. The washer is going to look something like that. Each cross-sectional slice is going to be a washer. As we get up towards the top of this, the top of this solid, the hole in the middle is going to be quite wide versus down at the bottom, right in here, those little slices, those little washers, the hole is very small. So that's what and I'll put the axis of revolution. That's what the cross-sectional slices look like. And here is that axis of revolution. And these are, of course, right, the filled in with that hole in the middle. So that's what we're looking at. But the area of a washer, and this will be, the thickness of this washer will be with respect to y, because we're taking slices. Let's write it right here. The thickness is definitely a delta y. And, oh, you know what we didn't talk about is this intersection point right here. These intersect at 1, 1. I think we can see that from the graph, or we could set those equal to each other. It's off, but they definitely intersect at 1, 1, and then this is the origin at 0, 0. So we know on this graph that this is 0 and the top of the solid is at 1. So a cross-sectional slice. So let's think about what a cross-sectional area looks like. It's going to be a function of y, and because it's a washer, it's going to be pi times the outer radius of that washer squared minus the inner radius of that washer squared. So let's get in here and think about what would the outer radius. So for every slice, I'll go ahead and do in red. I'll do my outer radius. My outer radius is going to be that length, and my inner radius, let's use blue. My inner radius of each slice is going to be this little length right here. That's the inner radius. And it's hard to see in here, but I'll put a little blue and I will put a little red on the solid there as well. And you can see that inner and that outer radius. And here's the outer radius. I'll make it in 3 spots. I'll draw it. And here is that inner radius, doing blue for the inner radius and red for the outer radius. So we can see those on the visual. What do those look like to put into the formula? So let's think about that. How do I calculate the length of that outer radius? Well, this is where, kind of going back to how we calculated areas, that length right there would be the function on the right, which is this function, and minus the function on the left. But we do actually have to think of this as, of course, it's not really necessary to write it this way, but I will. We do have to think of it as x equals y. And in fact, because we have to write these radiuses in terms of y, because this area needs to be a function of y based on the cross-sectional slices and their thickness along the y-axis. So over here we have y equals x squared, but that's the same as writing x equals y squared. Those two functions we can manipulate a little bit, and I'll circle just the one we need. We can manipulate those functions a little bit and write them as functions of y or functions of x. And so our outer radius, in this case, our outer radius is going to be y minus 0, or just y. So it's the function on the right minus the function on the left. And our inner radius, I'll do that in blue, is going to be y squared minus 0, or just y squared. Now let's take those and put those into our formula and get our area formula of a cross section. It's going to be pi times the outer radius, which is y, quantity squared, minus the inner radius, which is y squared, squared. And so my area formula, let's keep this all on the board here so that we can do it. My area formula is going to be pi times y squared minus y to the fourth. And now we're ready, right? Now we've done all of the setup, all of the geometry to graph it and visualize it and figure out if it was a washer or a disk and what those radiuses looked like to calculate the area formula. And now the volume of the solid is simply going to be the integral across where we start taking those slices. So we start down here at 0 and we take slices all the way till we get up to 1. So we're taking slices that look like washers from 0 to 1, and their formula for the area of each of those washers is pi times y squared minus y to the fourth, and it's a thickness of delta y, so we're integrating with respect to y, and that is the formula for setting up the area, the integral of the area function. And so the volume ends up simply being pi. Let's go ahead and integrate. That's a pretty simple integral. Basic integral rules, just our power rule. So y cubed over 3 minus y to the fifth over 5. And we're evaluating from 0 to 1. I'm going to zoom in. I'm zoomed way out. It's hard to write like that. So let's go ahead and zoom in a little bit. So that's just pi times 1/3 minus 1/5. Do a little common denominator work there. We get 5/15 minus 3/15, which is 2/15. And our final answer times pi. So 2 pi over 15 units cubed of volume. Okay. Let's get that all on the screen so we can see it. So that's how much volume is in this solid that we drew right here. I want to end by re-putting this step-by-step process on the screen. And we will do another video with some more examples. We will revolve. We've done a revolution now around the x-axis and the y-axis, and I will show you how to do revolutions off of the x or the y-axis around different horizontal or vertical axes. But they are the same process, exact same process that we will go through. Our calculations for the radiuses may have a little bit of shifting if we're off of our x or y-axis.